All right, so we are starting topic 8.2, which has to do with heat transfer. And we are going to start the lesson with a meditation to understand energy at a deeper level. So we'll take 15 minutes to meditate before we start this lesson. And this is just a reminder, there is also a self-study guide for topic 8.2. And in the self-study guide, after you complete it, you can check the answers to your questions. So we are giving you in the slides everything you need to learn this unit by itself. So hopefully you did the meditation and you are aware of the 5 elements of nature, the fluids around us, the solid matter around us, the energy that comes from the sun, and the space inside and around us. So when we talk about heat transferred, we think about, if it's through solid matter, we talk about conduction. This is the definition of conduction. Definition of convection, transfer of heat in a fluid by motion. Warmer fluids go up and cooler fluids come down by difference of density, and this creates the currents, right? The winds. And radiation, we look at the concept of emissivity here. Yeah? The ratio between the power that is incident and the power that is coming out, that is called emissivity. So these are the concepts, and the difference between internal energy, which is the total energy of the microscopic random kinetic energy, and the intermolecular potential energy of the particles in a material, and the thermal energy, which is only the kinetic energy portion of that. So the thermal energy does not include the intermolecular forces that we consider when we talk about internal energy. So these are some of the words that are there also shared in the presentation that you need to remember and use properly. We will see some laws. So careful experiments on the radiation emitted by black bodies. This was Stefan Boltzmann experimenting with, in a lab, experimenting with bodies at different temperatures and measuring the power radiated per unit area. And these are the conclusions. The energy occupies a continuous spectrums of wavelength with a sharp limit in the shorter wavelength. So this is short and this is long visible light. There is a sharp limit in the shorter range of the wavelengths, right? And all these spectrum of radiation include infrared radiation, invisible radiation that is outside of the visible spectrum. Second observation. There is an asymmetry intensity variation in the wave that peaks forward towards the smaller wavelengths. And the intensity peak at a wavelength can be predicted by the temperature. And this is something that becomes a law which we will cover soon. So this is just a bullet points of what was observed to explain these shapes. These come from experimental evidence. There is a very, very good a long 30 minutes long explanation on heat transfer and black body radiation by Chris Donner. That is an option. You can watch that video. It's linked to your slides. But the law that we were talking about is this Wien's law. We said the peak radiation is related to the temperature. If you look at these graphs, the peak radiation, that means the wavelength, is connected to the temperature. High temperature, the radiation peaks here. Lower temperature, the radiation peaks further away. So there seems to be an inverse proportion or an inverse law between the maximum wavelength and the temperature in Kelvin, and that constant of inverse proportionality is an empirical constant, B, and I leave you to calculate the units of B. They should be here. Okay, let's put them. What are the units of B? let's see. So this is meters equals something divided by Kelvin. So this has to be meters Kelvin, right? So the Kelvin goes away. So this is meters Kelvin. This is how we work out the unit of P. It's an empirical unit. What is important about, an empirical law, what is important about this law is that if we look at the light coming from a star and we identify the peak wavelength, because that's where the intensity becomes maximum, then we can know the temperature of a star. So this is an important idea because it connects something that we see with something that we have no way of measuring, which is the temperature of the atmosphere of that star where the light is traveling from. And this is one way we have to classify stars according to the temperature. So it's important for astrophysics. Another law that comes from Stefan Boltzmann's experiments, again another empirical law, is that the power emitted by a star could be, or any black body, or any body that has a certain emissivity. If it's a black body, the emissivity is 1, is proportional to the area and proportional to the temperature, to the power of 4 of the temperature. So this formula, this equation, if we know the area and we know the temperature, we can predict the power that it will emit. And if you look at this from the, again, the astronomical perspective, if we know the temperature because we know the wavelength, we know the temperature, and we measure the intensity, we measure the power that it's reaching the Earth per unit meter, then we can predict or measure the area, not measure but determine the area of a star, the size of a star. Another killing idea. So these are connections between these laws and astrophysics. That's why I say the topic 8 is very important to understand well, to connect this to astrophysics. A must. When you get to this slide, please watch the parts A and B of black body radiation, how Mr. Kahn solves these problems, because in solving problems, it's when you understand the concepts. Okay. Solar constant. What is a solar constant? It is a constant relative to the Earth. It is the 1.36 kilowatt per square meter. That is the mean solar radiant power per unit area, or the intensity of light energy coming from the sun for rays that are perpendicular to the top of the atmosphere. So these rays are perpendicular to the atmosphere, so the amount of energy per square meter that we receive on average is around 1,360 watts. That means 360 joules per second coming from the sun every square meter. That is an enormous amount of energy. I think I read somewhere that in a single hour, the Earth gets all the energy from the sun that we need to power the Earth for a whole year. So that is the amount of energy that is coming from the sun to the Earth every hour. An enormous amount of energy. If only we could capture that and use it properly. The concept of albedo, another concept that it's probably new to you. It is a number. It is a ratio between the scattered power, or the radiation that is bouncing off the surface, compared to the incident radiation. So if all the radiation that is coming from the sun is absorbed by the Earth, then the albedo is 0 and the Earth would be a black body. But that is not true. Part of the radiation that comes from the sun bounces off and part of it is absorbed. So the percentage of radiation that bounces off the surface of the Earth compared to the percentage of radiation that is coming into the surface of the Earth If you divide this by this, you get a percentage, and that is an albedo. So for instance, it depends a lot on the color, but white surfaces like snow have very high albedos. Snow, fresh snow, which is very white, is almost 80% of the energy bounces off. Sand, 40% bounces off. If it's dry, if it's wet, it is absorbing energy. Interesting, because the albedo has to do with global warming, right? So if we could change, for example, if we could paint the poles black, we would absorb more energy because we are changing the albedo of the Earth, and that means that the global warming would be enhanced, would be increased, because more energy is being absorbed by the Earth. So the albedo plays an important role in the temperature balance of the Earth. Again, must watch 3 minutes of a problem of how to solve albedo. This is the average albedo of the Earth, but as I said, different colors have albedos that range from 0 to 1. You can never have 1, and 0 is a black body, so you can't find very easily black bodies on Earth. And what is the greenhouse effect? Here you have a very nice video which you can watch, Chris Donner explaining the greenhouse effect. Another interesting video on how the clouds affect the models. But basically, to explain greenhouse effect, there is a word that you need to understand and use, and that concept is the concept of resonance. So what is the greenhouse effect? In simple terms, the energy that comes from the sun, right? All this energy that is coming from the sun, solar constant, coming from the sun. Part of it is reflected back due to the clouds. The presence of the clouds reflects the energy back off. The surface of the Earth reflects some energy back, but some energy is absorbed by the Earth. Some energy is absorbed by the atmosphere. And the Earth re-radiates this energy back to the atmosphere, with the problem that the atmosphere will have gases that resonate, greenhouse gases that vibrate in sympathy with this infrared radiation. That means they are absorbing that energy and retaining it in the clouds, in the atmosphere. Greenhouse gases like carbon dioxide, water vapor, methane, you know, all these gases, which are great because they keep the atmosphere warm, and they keep us warm at night, and they make life possible. But if you are increasing the presence of these gases in the atmosphere by burning fossil fuels, for example, then we have gases that are trapping this energy that wants to go back to space and creating the enhanced greenhouse effect. So that is the connection between greenhouse effect and the concept of resonance, which we have covered in waves. So that is in very simple terms. We know what greenhouse effect is. I just want you to look at the way problems are being solved again by Mr. Khan, and maybe this is an important video to check to learn more about the enhanced greenhouse effect. That means the global warming, excessive global warming, a big problem that we are facing. So by the end of the slides, by the end of the lesson, not by the end of this video, by no means, but at the end of the lesson, you should be able to describe convection, conduction. You should be able to understand Stefan Boltzmann's law, Wien's law, albedo, emissivity, and solar constant. Those names, you should be able to define them, use them to solve problems, explain the greenhouse effect. Don't stay with my explanation. Watch Chris Donner. Name the greenhouse gases. This is an IB. These are all the IB syllabus points. So this is what you are expected to know for the IB, okay? So make sure you know them. And then describe the energy balance between the Earth's surface and the atmosphere, which has to do with resonance and greenhouse gases. So this is what topic 8.2 is about. I want you to start this again from the very beginning, looking at the meditation and then looking at the self-study guide and doing all the problems that I posted in the OLP. Okay? Have a wonderful journey.